Hey there, this video is working problem set 37 in the thermodynamics unit entitled Entropy, so let's get started. Alright, starting off. Question 1 asks, what does it mean for a reaction to happen spontaneously? So the textbook definition says something along the lines of a spontaneous reaction, once it gets started, will continue without the addition of extra energy. I like to define it as saying that a spontaneous reaction is just something that's going to happen. A spontaneous process is something that happens. Non-spontaneous things don't happen. So I'm just going to write happens here. Now it's important to understand that there are some things that happen at certain conditions and don't happen at other conditions. And so it's not, when describing like a situation, to ask if it's spontaneous or not, well, that depends on the conditions that it's under. And I'm sure that will come up later. If not in this problem set, it should come up in later ones. But yeah, so that's how I'm just going to say a reaction is spontaneous when it happens, but you should understand the textbook definition as well. All right, state the second law of thermodynamics in one sentence using your own words. Just make sure this is recording. It is. Okay, using your own words. Use any appropriate equations. So the second law of thermodynamics is that the total change in entropy of the universe is greater than or equal to 0 at any given time. And that's because the delta S of the universe is positive for a spontaneous process, and again, only spontaneous processes happen. So if nothing is happening, it would be 0, but if anything is happening, which is more realistic, that something is happening in the universe, then the delta S of the universe will be positive. So I'm going to say for spontaneous. All right, and then state the third law of thermodynamics in one sentence using your own words. Use any appropriate equations. So the third law of thermodynamics is that the entropy equals 0. Now again, that's not change in entropy. That's just actual entropy. Just the value itself is going to be 0. For a perfect crystal, at 0 Kelvin. And that's going to bring us to number 2. So so this says define entropy and use any appropriate equation. So I'll talk about how I just talked about entropy, but in relation to number 3, the actual equation to calculate entropy, this is the one that was carved on the guy's grave. So entropy equals the Boltzmann constant times the natural log of W. And W is the number of microstates. Now we're never going to ask you to figure out the number of microstates of something, but if you're given the number of microstates, it could realistically be asked of you to use this equation, because you literally just plug in the constant, which is on your equation sheet, ln of the microstates, and you get the entropy. And that's why for a perfect crystal at 0 Kelvin, how many ways are there to arrange a perfect crystal at 0 Kelvin? There's only one. So as a result, when you plug in 1 to a natural log, you get 0. So that's why your entropy would be 0 for a perfect crystal at 0 Kelvin. But define entropy. Entropy is a measure of the dispersion of energy in a system. So if energy has more, is spread out more, then it will have higher entropy. People like to say entropy is a measure of disorder, so that's not perfectly true, but it helps when you're thinking about it. So if you want to think about it that way, that's just fine. So entropy. So disorder is increasing in general in the universe, but why is it that entropy increases, or that things, I guess a better way to put it is, why is it that things tend to spread out in energy? So for example, I like to use the example of a stack of papers. If I have a stack of papers perfectly stacked and I throw them up in the air, is it possible that they come back down and land perfectly stacked? Yes, that's a possibility, but how many ways are there to arrange that? Only a couple. How many different ways are there, though, that I could throw them up in the air and they would just spread out randomly? Well, there's a ton, right? Almost infinitely more ways than them stacking up perfectly. So while it's possible for them to come stack up perfectly, there's just statistically there's a higher probability, a way higher probability that they're going to spread out. And that's why we see things become more disordered over time. Energy becomes dispersed. So I'm just going to write dispersion of energy. Okay, let's state 3 factors that affect entropy change. How entropy change is within each and why. Okay, so 1 is phase, right? Because if I'm a gas, I definitely have more ways to spread out and disperse energy than a solid does. There's more disorder. 2 would be, I would say, number of particles. If I take something and I react it and the phase doesn't change, but they split into more particles, entropy is increased. If they combine into fewer particles, the level of disorder is less, and so entropy would have decreased. 3, if I'm got 2 different molecules I'm comparing and one's significantly bigger than the other one, well, that has more ways to flip around, right, and manipulate itself, and so that's going to have greater entropy. And then there's a 4th one that was talked about in class, and called it rigidity. Basically, if you had like 2 isomers, these are both C5H12, okay, but this one could flip around and manipulate itself in different ways more than this one could, because this one, the way it's bonded, is more rigid. I know that's a terrible, there we go. So this would be have greater entropy because it's less rigid. Okay, describe 2 ways of calculating changes in entropy. All right, so let's say that I've got a reaction. A plus B goes to C plus D. If I knew the entropy values for each of these, I put that little knot there just because usually we're dealing with standard state. All right, if I've got the entropy values for each component in the reaction, I can calculate the standard entropy of reaction as the sum of the number of moles times the entropy values of the products minus the sum number of moles times the entropy values of the reactants. So we've done products minus reactants before using delta H's of formation, and now we're using entropies. Now these aren't delta S's of formation, right? They're just entropy values, and that's fine. But what you got to remember is that with entropy values for a pure element, well, I should say with delta H's of formation, for a pure element, it's in its standard conditions, the delta H of formation is 0. Is the entropy of 0 for a pure element at standard conditions? No, absolutely not. Why? Well, the entropy is 0 for a perfect crystal at 0 Kelvin. And so it's not going to be 0 for a pure element in its standard state. Okay? So you do have to have actual value for the pure element. But that's one way. Wow, bad. Okay, that's one way to calculate entropy of reaction. The other way is delta S equals, so on your equation sheet it says Q reversible over T. I'm going to replace that with delta H because we know delta H and Q are the same thing. Delta H reversible over T, what does that mean? That's the enthalpy of a reversible process. So I like to describe a reversible process for you guys as something where you're transferring heat and the temperature is not changing, or is changing negligibly. So there's kind of 2 situations where you'll be able to apply this equation, and that's a phase change. If you're at the temperature of a phase change, then you are adding heat and the temperature is not changing. And if you're talking about the surroundings, then usually there's no reaction in the surroundings, nothing weird is happening, but if I'm releasing heat into the universe, like into the world, I should say, the temperature of the world isn't changing. And so the second equation would be delta H reversible over temperature, with the caveat that it can only be applied in a couple of situations, but there's situations you'll see a lot. All right, number 3, which component in each of the following pairs has the greatest entropy? All right, so we have 1 mole of S2 and 1 mole of S8. So the first thing I'm going to think about is if one of these has more particles, it's definitely going to have more entropy, but they both have 1 mole. So they both have 6.02 times 10 to the 23rd molecules. So the number of particles is the same. So then I kind of listed here in order of importance. They're both gas. They have the same number of particles. So then I look at the size. S8 is bigger. And so S8 is going to have more entropy. All right, then I have 1 mole of S2 gas and 1 mole of S8 solid. All right, well, the phase wins always, and so gas is going to have more entropy. 1 mole of O2 gas, 1 mole of O3 gas. That's another situation just like the first one. They have the same number of particles, same phase. Look at O3 because it's bigger. 1 gram of O2 and 1 gram of O3. So in this case, the answer is going to be O2 because these are grams of each thing. All right, and I think about it, O2 has a smaller molar mass, which means 1 gram of it's going to have more particles because each particle weighs less, if that makes sense. And so as a result, 1 gram of O2 has more particles than 1 gram of O3, so that is going to have more entropy. All right, ice cubes melt in a glass of lemonade, cooling the lemonade from 10 degrees to 0 degrees. If the ice cubes are the system, what are the signs of delta S? System, delta S surroundings, and delta S the universe. Ice cubes are the system. All right, so delta S of the system. What I'm asking is, the ice cubes, do they become more ordered or less ordered? Well, they're melting. Yeah, if something's melting, it's becoming less ordered, so the entropy is increasing. The surroundings, what's happening in the surroundings, cooling the lemonade. The lemonade is just getting colder. Okay, there's no phase change or reaction. It's just getting colder. Well, if things just get colder, there's less energy in there moving the molecules around. Colder things have less molecular motion and therefore less entropy. So if I'm cooling something down and that's it, my surroundings are going to be negative. And then lastly, the universe. Excuse me. The universe, what's the question I'm asking with the universe? Some people like to think, oh, well, I know that delta S of the universe equals delta S of the system plus delta S of the surroundings. But in this case, that doesn't help because the system is positive, the surroundings is negative. So like, I don't know what that is without having numbers, but you actually do. Because remember, the second law of thermodynamics is that for a spontaneous process, which is one that happens, delta S of the universe is greater than 0. Which means, I mean, do ice cubes melt in a glass of lemonade? That's 10 degrees. Yeah, that's above freezing. So the ice cubes are going to melt, which means this does happen, which means delta S of the universe is positive. All right. Adding sidewalk deicer, calcium chloride, to water causes the salt to dissolve and the temperature of the water to increase. If CaCl is the system, what are the signs of delta S? System, surroundings, and universe? Well, so CaCl3 is the system. What's happening to that system? Well, it's going from solid, and then it's dissolving, so I would call that aqueous. Solid to aqueous. Aqueous has more disorder, and so it must be increasing in entropy, so positive. The surroundings is this, let's see, water, adding salt to water causes the salt to dissolve and the temperature of the water to increase. What did we just talk about? Temperature. If all you're doing is changing the temperature, increasing the temperature, increases the level of molecular motion, which is greater entropy, so delta S of the surroundings is going to be positive. And then delta S of the universe, does this happen when you put salt on ice? Or when I put salt in the water and it dissolves, water increases, that's something that happens, and so that's going to be positive. All right. Predict whether the entropy of the system increases or decreases in the following reactions. Oh, sorry, that A should have been put down below. But liquid water going to gas, okay, that's going to increase because of my phase. So first, again, I'm going to look at phase. After I look at phase, I'm going to look at number of particles if the phases don't change. So here, solid to aqueous, that's an increase because that is a less ordered state. Solid and gas goes to solid. So you're losing that gas in a solid, so that must be going down. Gas, gas, gas. So that doesn't tell me anything. So now I'm going to look at the number of particles. Here I have 1, 2 particles, and here I have 2 particles. I could keep going and look at like the size of these molecules, but in a reaction, the mass is conserved. So the size isn't really changing collectively. And so here I'm going to say I don't really know. I'm going to say it's probably close to 0, but without actual numbers. Actually, I don't even really like close to 0 because I don't know the number. So I'm just going to say I don't know. You can't tell just from looking at that. Here I've got solid to gas, so it's increasing. Solid and gas go to solid. That must be decreasing again because the phase. Gas goes to solid, must be decreasing, and gas goes to gas. So that doesn't tell me anything. So here I have 2 particles, 1 particle going to 2 particles. So that's 3 going to 2. So that's becoming more ordered, less entropy. All right, where are we at? We got a ways to go. All right, particular reaction is spontaneous and has delta S of reaction of negative 163 joules per Kelvin. What must be true about delta S of the surroundings? All right, so I know that delta S of the universe equals delta S of the system plus delta S of the surroundings. If I don't put a subscript, that implies system. All right, so what do I know about these things? Do I know anything about delta S of the universe? So it doesn't say anything except that the reaction is spontaneous. What does that mean? This has to be positive. Then delta S of the system, okay, in this case we're talking about a reaction, so the reaction is the system, is negative 163. What must be true about delta S of the surroundings? Well, if the system is negative 163, but the universe is positive, what does the surroundings have to be? Well, it has to be bigger. If it's 163, they're going to add up to 0. So in order to be positive, I need this to be greater than positive 163. Okay, and again, that's joules per Kelvin. All right, similar question here with one more extra step. Particular reaction releases 25 kilojoules of heat into the surroundings, which are 27 degrees Celsius. If this reaction is spontaneous, how does this limit the possible values for delta S of the reaction? So we know the universe equals the system plus the surroundings. What do we know? Well, we know that it is spontaneous, so this must be positive. So I'm actually going to do this. I'm going to write that this is positive. I'm going to say that everything on the right side has to be greater than 0, if that makes sense. Because if all of this is greater than 0, this must be positive. Okay. And we're trying to figure out about delta S of the reaction. So that's our system. And I'll write reaction. And then I need to know something about delta S of the surroundings. Well, how do we figure out delta S of the surroundings? We talked about that up here. For the surroundings, because I'm adding heat into them or taking heat out of them and nothing's changing the temperature, I can use the delta S. I can use that the delta S of the surroundings equals the delta H of the surroundings over the temperature of the surroundings. What's delta H of the surroundings? Well, the reaction releases 25 kilojoules of heat. Okay. So if the reaction is releasing 25 kilojoules of heat, then the delta H of the reaction is negative 25 kilojoules. But I care about the delta H of the surroundings, not the reaction. So the surroundings would be absorbing 25 kilojoules. So that must be positive. And the temperature of the surroundings is 27 Celsius, but I want to use Kelvin, so that's 300 Kelvin, which means delta S of the surroundings is 0.0833 kilojoules per Kelvin. Okay, so I could rearrange this inequality, and I could say, I could subtract that over, or I'll subtract this over. I get negative 0.0833 kilojoules per Kelvin is less than delta S of the reaction. Okay, and so that should make sense. Wait. Yes. So I know that the surroundings is 0.0833. So the universe has to be positive. So the system, the reaction, it could be lower than, it could be negative as long as it's not a larger magnitude than this, because if it was, it would make this number negative. So negative 0.0833 is the smallest value that it could be, and so it must be greater than negative 0.0833. Let me just, yeah, okay. Mercury is a liquid at room temperature and freezes at negative 38.9 degrees Celsius. What's the entropy change for 50 grams of mercury? Freeze, if its enthalpy of fusion is 2.29 kilojoules per mole. Well, remember, for a phase change, how can we calculate entropy? Again, it's delta H over T. So the delta S of this phase change is going to equal delta H of this phase change over the temperature of the phase change. And it tells me that its enthalpy of fusion is 2.29 kilojoules per mole, but that's not my delta H because fusion is melting, and I'm not melting the mercury, I'm freezing it. And so my delta H is actually going to be the opposite, or the negative value of that. And the temperature of my phase change is negative 38.9. Add 273 to that, I get 234.1 Kelvin, which gives me kilojoules per mole Kelvin. Okay, just make sure that number's right before I move on. Oh, okay, so, but is that the entropy change when 50 grams of mercury freezes? No, because that's per mole. So this is the entropy change when 1 mole freezes. So how would I figure out for 50 grams? Well, I would just multiply it by however many moles 50 grams is. So the total entropy change, first do 50 grams, and 1 mole of mercury is 200 grams. So this would be 0.25 moles of mercury. So this is for 1 mole, so then I could say the total delta S is going to be 0.00978 kilojoules per mole K times my 0.25 moles, and that gives me, see if that was right, yeah, that gives me that the delta S when 50 grams freezes is going to be 0.00244 kilojoules per mole, or I could say it's negative 2.44 joules per mole. Sorry, I shouldn't be saying per mole, it should be per Kelvin. The moles canceled out. Does it make sense that this value is negative? Well, the mercury's freezing. It's becoming more ordered, so yes, entropy should be negative. All right, the normal boiling point of ethanol is 78.3 degrees Celsius. The enthalpy of vaporization is 38.56 kilojoules per mole. What's the delta S of the system when 68.3 grams of ethanol condenses at its normal boiling point in 1 atm? Okay, so this is literally the exact same problem again. We've got a phase change, so delta S equals delta H over T, which in this case, delta H is, the P of vaporization is, and are we vaporizing? No, we're condensing. So again, I need to flip the sign on that. So negative 38.56 kilojoules per mole. Temperature 78.3. It's 273. I got 351.3 Kelvin. That gives me negative 0.1098 kilojoules per mole Kelvin. But again, is that my total entropy change? No, that's my entropy change for 1 mole condensing. But I'm not condensing 1 mole, I'm condensing 68 grams. So I've got to figure out how many moles that is. And 1 mole of ethanol has a molar mass. Let's see. 1 mole of methanol has a molar mass of 38.5, oh no, of 46. Excuse me, 1.485 moles. So the total delta S is going to equal 1.485 moles times negative 0.1098 kilojoules per mole Kelvin. Delta S equals, I just changed the units in my head, negative 163 joules per Kelvin. Okay, sweet. All right, number 10. Following reaction plays a key role in the destruction of ozone in the atmosphere. The standard entropy change for delta S of the reaction is 19.9. Use the standard molar entropies in Appendix 4 to calculate S naught value for CLO. Okay. So we've got a reaction. They give us, we know the total delta S of the reaction equals 19.9 joules per mole K. And we should remember that that is going to equal the entropy values of the products minus the reactants. And they want us to look up everything. Let's look up that one, look up that one, look up that one, so that we can find that one. And you could ask, well, why don't we just look up that one? You're right. You could just look up CLO as well, but that defeats the purpose of the problem. So we know that delta S of a reaction equals S naught products, not there technically, minus S naught reactants. So that's going to be S naught of CLO plus S naught of O2 minus 1/2 S naught of Cl2 plus S naught of O3. So if I look up those values, this is the one I'm solving for. And I've got O2, which 205. Okay, and all of these are in joules per mole Kelvin. Cl2 is 223. And like O3 is 238.8. Okay, so I can just, this is just algebra. Oh, and remember that I know that this delta S of the reaction is 19.9. So I'm just doing the math now. Okay, and when I did the math, I got that S naught of CLO is going to equal 165.2. Again, these are all in units of joules per mole K. Okay, and now 10b wants me to calculate delta S value for the conversion of ozone to oxygen, just like this. So again, I can just do products minus reactants, which in this case is going to be S naught, 3 times S naught of O2 minus 2 times S naught of O3, again, just products minus reactants. So that's going to be 3, and we just found out that O2 would be 205, and O3 is 238.8. So That gives me a delta S naught of reaction equal to 137.4. And those are all in joules per mole. Okay. Beautiful. All right, so that is problem set 37, and hopefully you find that helpful.